session name? Yes. It's a operators forum in this region, Asia Pacific. That's why it's APOPS. APOPS is co-chaired by three of us. Philip Smith over there sitting, and Tomoya Yoshida, probably somewhere, and myself. So we have two APOPS sessions in this week. This is a APOPS one, and tomorrow morning we have another APOPS session. So in this session, we have two talks. First up is Geoff. Geoff from APNIC. He will talk about IPv6 performance. Geoff, please.
Good afternoon, my name is Geoff Huston. I'm the Chief Scientist at APNIC, which means I get to do things that I like doing and occasionally talk about them at places like this. So you've heard, if you've come to any kind of APNIC meeting in the last 20 years or so, all of these exhortations, you must use v6. And of course the real question is, are you bullshitting us? I'm like, what if v6 runs like a dog? Why are you telling us to run this protocol? Which is a fine question. And I kind of got interested in this question because it's come up a few times. Paul Saab from Facebook reckons that when they loaded up v6 into their apps and have Facebook on v6, he reckoned it was faster. So I'm a bit interested in this. It's kind of, is it really faster? Can we find some numbers? What can we find out about v6 performance? So that's what I want to talk about this afternoon. There are many things to measure on the internet. You know, how many cat videos, all that kind of crap, right? There are many things you can measure. There are many things that you should not measure. Number of cat videos are included. One of the things that I was really interested in is these two really just basic questions about v6. So when you talk about performance, what you're really looking at is, do connections work? If I send you a SYN, we're talking TCP now, we're down and dirty in the protocol. When I send you a SYN, I want you to ACK my SYN, and then I'll ACK it back and we're in business, right? But sometimes what you see is the SYN gets sent, but there's no corresponding sort of handshake that gets concluded. There's something failing. So I want to talk about and look at this issue of connection attempts and the success or otherwise of them. And then secondly, I want to get right down into it and actually try and look at the question, is v6 faster? Do the packets squirt through the network faster than v4? Do they, violate some speed of light principle or something because they're magically 6, not 4, and make them go, oh, so much faster? Or not? So those are the two kind of questions we want to look at today. How do you measure a few 100 million people? And the first thing about this is most of these systems suffer from measurement bias. The problem is if you sort of put something on a web page, you get to see the visitors to that web page. So we put on some stuff on APNIC's web page some years ago measuring v6, and we were amazed to see that something like 30% of the folk who visited APNIC were capable of running v6. Only geeks ever go to the APNIC page. So we were measuring basically geeks inside machine rooms or whatever, and it wasn't a real measurement. It was just this straight up measurement bias. So how do you try and cover most of the internet? And if you think about it, there's one question that I suppose if I ask, you'll immediately go click, and the answer is, how many of you have seen an ad? Every last one of you. Even in North Korea, they look at ads. They do. And the beauty about ads, if you sort of strip them apart a little bit, is that it's not just an image. It's an image with a script. And the beauty about the ads are, you only pay when they click, but the script always runs. So in essence, the way we get this done is, we put the script inside the ad, and the ad machine goes overboard in trying to present our ad to as many people as possible so that a few people will click on it. The crappier the message and the less inclined you are to click, the more ads get presented. Because Google want my money, and that's perfectly fine. So these days we do around, I think it's on the next few slides, we do quite a few ads a day, and each of these ads sets up a test. And the test is really simple. Get this URL. Now, at the back end of the URL is just a 1-by-1 image. Tiny, tiny, tiny thing that never gets displayed. But to get that URL, you've got to resolve the name in the DNS, and then you've got to make a connection to my server because it's my name. So you're talking to me, and my machines are heavily instrumented. I log every packet, and I keep the time. I keep bloody good time. So I know what you're doing because I'm seeing the other end. So I examine everything I see. We use Google. If you're doing the advertising business, Google kind of defines advertising. We've been running this for many years, and for some time we were doing a few 100,000 ads a day. After some work with Google, and my thanks to Warren Kamari and Dr. Vince Cerf on this one, because they've been unstinting in their support, Google decided late last year they wanted to see the capacity of our servers, and all of a sudden, from doing a few million ads a day, they decided to test us at 12 million. And after we fell over and caught our breath, we thought, oh, gee whiz, that was an experience. So yes, we are doing around about 10 to 12 million measurements a day on some of the heavier days. So we get a lot of sample points drawn from literally all over the internet. Now, one of these experiments is pretty easy. This URL can only be fetched if you have v6. And the other one says, I don't care which protocol you use. So this is a log scale, so it makes them a bit closer than they really are. The top line is the number of ads per day. It's exactly the same as this, but in logarithm scale. Everyone remembers logs, right? It's called maths. Check it out. If I make it into a log scale, you kind of see it's a little clearer. But what we measure is that v6 penetration in the internet on the whole, once you get rid of the selection bias, and there is a selection bias, but once you get rid of that, it's not 10%, it's about 4 or 5%. That's still a nice number. And that's kind of the green line is the v6 capable. But that's not really what I want to talk about. What I want to talk about is that initial TCP handshake. Because don't forget, I've given you a URL, and you've done the DNS dance, that's fine. You've decided that the IP address is me, thank you very much. And now your next job is to open up an HTTP connection saying, give me that 1-by-1 pixel, I really need it. You really do. And the way this is going to work, of course, is irrespective of whether you're doing SSL or not, you've got to open up that initial connection. So I'm actually looking at that initial connection, and I'm trying to figure out what goes on with what I'd call naked sins. Because with TCP, you send me an opening connection packet, a SYN. It's got the SYN flag on. I send you back a SYN, because I want to be sinful too, and I send you back an ACK to say, yes, I got yours, here's mine. Now, you're meant to reply with an ACK, and then off we go down into fetch this URL, let's have fun. What happens when I don't get the ACK? Connection fails. We all just walk away going, well, that wasn't much fun. So what's the prevalence of this? So I want to look at two data sets to see if this is getting better or worse. The first data set was collected in 2011, back in the dim, dark mists of prehistory of v6. And at that time, Microsoft still made operating systems. I don't think they do anymore. Microsoft still have browsers that people use. I'm not sure that's the case anymore. But one of the things at the time, and this was Windows XP, was they were really keen on two v6 tunneling technologies, Teredo and 6-to-4. And there was a lot of it. And for many folk, that was the only way you got to v6. I've also collected another massive data set across most of last year, and there's a small amount of missing data, but it encompasses most of the last sort of 13, 14 months. And I'd like to compare these two. If you're in 2011 and you were thinking of deploying v6 as a service, you were certifiably insane. You really hated your customers and you wanted to put them through the worst possible experience you could ever actually manufacture. 4 out of 10 connection attempts failed. I'm like, not even cellular radio is that bad. Not even Wi-Fi in this room is that bad. 4 out of 10 fail is sort of epic fail. That's the green line. The red line is V4. So, you know, V6 at the time was complete and total crap. Why? Why was that so incredibly high? And oddly enough, what was going on with V4 anyway? So that first question, what's going on with V4? Why is there a failure rate? Doesn't V4 always work? It decreased when the volume of experiments increased. So it was some kind of percentage thing going on. And one sort of theory was that this wasn't really me, it was the level of background radiation. It was just the fact that a lot of folks scan the V4 address space, or so I thought. And you know, it's just, that's the base level of connection breakage. I'm like syntax notwithstanding, I'm actually unhappy with that explanation. I am truly unhappy with it. How much do we measure of asymmetric connection failure? And I'll bet none of you do. If I can reach you, it doesn't mean that you can reach me. And what's going on now is that Google can reach you and set you up with an ad, and then you try and reach me, and you can, and I try and reach you, and I can't. And that happens in the V4 network around 1 in 500 times. Not everybody is connected to everybody else. That's weird. That's truly not what we expected. I have a phone, it can ring anyone. Well, no, it can't. 1 in 500 things won't work properly, and that's what you're seeing with V4, and that's strange, and you should fix it. But that's not the big problem. The big problem was at the time V6, and in essence, we started to get some clues as to what was going on because I was trying to give folk running Teredo a helping hand. And rather than using the Teredo servers provided by Microsoft, I thought, I'll be really good, I'll run my own. It was so reliable, it broke a few times. Whenever it broke, the spike went really high. So what I was seeing was Teredo. So because Teredo uses a family of source addresses, 2001:0:/32, I can take all the incoming Teredo folk and put them in one bucket, the bucket of shame, the purple line. The one that says Teredo is complete and total shit. I'm like, there's just no way of describing it. If you're running Teredo, you shouldn't have bothered. 6-4, that well-known tunnelling protocol, still failed at around 30%, 1 in 3. So that worked really well, didn't it? Down the bottom was actually V6 native. So this tells you a couple of things. But the major lesson you should take away from this is that almost all forms of autonomous tunnelling using automatic rendezvous are crap. Think about Lisp just for a second and think about what I said. All forms of tunnelling tend to be crap when they're using basically autonomous rendezvous, because you don't know exactly where the packets are going or why. The encapsulation just breeds horrendous asymmetry and the failure rates express it. No wonder Microsoft removed Teredo. They had to. And 6-4 was truly an invention of the devil. Thank you, Brian. You know, it was great, but it's not the right thing. Is Brian here today? Brian Carpenter, University of Auckland? I can say it. It's shit. Sorry, Brian. Why was 6-4 failing so badly? Not the least of which it was tunnelling. The other thing is, it surprised all the firewalls. There are a lot of firewalls out there, and this wasn't TCP, so it wasn't protocol number 16 or whatever it is. It wasn't UDP, it was protocol 41. You have firewalls, protocol 41 is an invention of the devil, you block them too, as does everyone else. So all the incoming packets were put in the sin bin of death. So you could send out a sin, but you were never ever going to get the SYNAC in 6-4. So, you know, 10 to 20% failure rate at the time, this was terrible. V6 back in 2012, failure rate of 5%. And you think, well, by comparison, that's really good, right? By comparison, that's fantastic. Only 1 in 20 people, you lot over there, died. It's still not very good, is it? You'd never put out a service with a 5% failure rate. What's going on? Some machines have no idea about scope. Linked local is a local problem. Don't tell me your linked local address. I don't know what to do with it. Unique local source addresses are not meant to be sent to the world. The rest of us don't know what to do with it. Deprecated site local, I'm sorry, excuse me, that's just bullshit. And 1F02D9, typo, you just can't get it right, can you? The good news was we stopped using 3FFE, so what? So what you saw was it wasn't really typos. Most of that failure was structural. Have we got any better? So let's move on to the data set from all of last year and a bit of this year. Google have really been working very hard. I've got 40 million endpoints in V6, which I think is a reasonable sample point, drawn from all over the world. The failure rate, 1.3 million. You've gone from 5% to 3% failure. I'd like to say it's well done, but in absolute terms, none of you would survive as an ISP with a 3% failure rate in V4. None. So it's still crap. What's going on? Here's the failure rate, and this is a bit interesting. 12 months ago, 5% failure. 1st of September, things changed a little bit. And this is, again, one of these interesting areas. Google started to say, look, you can't write ads in Adobe Flash. You have to get with it and use HTML5. Groan, moan, groan, HTML5. All of a sudden, I get to see a whole bunch of mobile systems that didn't like Adobe Flash, and I get to not see a whole bunch of Windows systems. And interestingly, the failure rate's got a whole lot better. There's a clue going on there somewhere about the combination of Explorer and Flash that I don't really want to go into here, but you can draw your own conclusions about this. It was crap. So what about 6 to 4? Was this any better? 7.6 million 6 to 4 addresses. That's 20% of all the V6 is still running 6 to 4. Get with it, guys. Why? Because 6 to 4 still sucks. It's got a failure rate of 9%. This is just unacceptable. So if you look at all of this together, the top blue line is 6 to 4 failing like crazy, and it's not getting any better. The red line at the bottom is when you remove 6 to 4 and things look a little bit better. So it seems that 6 to 4 is the problem. Have you got the message? So let's actually just have a look at 6 to 4 again, but let's look at it differently. What's the percentage of folk still running Microsoft platforms running 6 to 4? And the good news is they're dying out really quickly. A year ago, 45% of everything I saw had 6 to 4 and preferred 6 to 4 when making a connection. That's really horrible. Last week, I'm down to 5% of the world is running 6 to 4. Well done, the world. Because, that 20% failure rate we're seeing in 6 to 4 or so is now just in a very small fraction of machines. So, stop using products that use 6 to 4 and we'll all be much, much happier, and V6 will be a whole lot better. So that's the first message. What about the rest? Those 20 million unique V6 addresses that I looked at, 142,000 was 6 to 4. There are still 138 people using Teredo. We should hunt them out and give them a new machine. Just give them something else. It'll be better. Some 68 people are still very confused about linked local. Doesn't matter how many times you teach them, they just don't learn. 834 haven't bothered using an address that's been allocated. So they're kind of shooting into the dark. I don't know why they're using V6. Nobody can talk to them. They are completely unallocated. And another 1,200 are using addresses that aren't announced in the routing system. I'm sorry, guys. If you want to be reached, announce it, right? Otherwise, we don't know who you are and we can't talk to you. So of the rest, 319,000, they were drawn from 216,000 unique 64s and they have a problem. Who are they? Well, these are the worst offenders. I do note there that if you're a customer of Mediacom, you folk in the US, if you're running V6, I pity you, your failure rate's 1 in 3. The Cultural Centre in Mexico, 97% failure rate. Admittedly, I only sampled them 300 times, but that is enough to point the finger of doom at them. And if you happen to see your AS number there, and there is an unfortunate there from Australia, you really should be doing something about this, because this is not a service. If you're listed here, the stuff is chronically bad, and you might be able to fix it. So I'll give you another chance. If you see yourself, do something about it. If you know someone on this list, let them know they can do something about it. So on the other side, we've got the actual list of folk who managed to do it right. Yes, it is possible at the University of Iowa to be sampled 2,000 times and every last one just works. So I'm not after a mythical ideal of perfection. These folk, absolutely none of them ever failed any connection attempt. So, you know, Rupert Murdoch's Foxtel actually does manage to do it right. It's about probably the only thing he does. Sorry, he's not my favourite man. But the rest of it, if you're on this list, that's very good. Pat yourself on the back, you've actually done the right thing, including SprintLink. So, you know, it is possible to be a big provider and get V6 right. So these folk actually got it right. What about V4, the failure rate in 2011, 0.2%? No different. The failure rate now, after measuring it 446 million times, because there's a lot of V4 out there, was still 0.26%. And this is asymmetric failure. That's the daily figure across the year, and yes, I'm sorry, for a certain period I wasn't running packet captures. My poor machines were running out of disk space. Thank you, Google. But on the rest of it, what you see is it's astonishingly constant at around 1 in 500. I don't think this is local machinery. I think this is the fact that not everyone can speak to everyone else all the time. We don't know when we're not running a full set of routes. We don't understand what a default free zone is. And every single provider only sees a fraction of the whole. And it differs provider by provider. So you can send me a packet doesn't necessarily mean I can send a packet back. And that's what we're uncovering inside this data, that asymmetric connectivity is an unceasing factor. How do you know you've not got the full route set? Wow. Nobody can answer that question, least of all me. What's the full route set anyway? There's no list. Well, you could say, well, is it level 3? No, probably not. Is it AS701 or is it NTT? I don't know, and neither do you. But are any of you running a complete and total route set? Probably not. And this data reflects that. There's at least 1 in 500 where you can see me and I cannot see you. Now, as long as you can get to Netflix, YouTube and watch cat videos, maybe you just don't care. And that's okay too, I don't care either. But there's something structural underneath this that as operators we really should think about. To what extent is there asymmetric connectivity fracturing in the internet and how big is it? Gee, that's a good question. Let's have a date this year in September, and let's talk about that in the presentation pack, because I think that's a question we all want to answer. V6 comparison, the V4 line is at the bottom, so V6 is still crap. You know, it should be down there with the red. It's not. That no matter how you look at it, V6 is nowhere near as robust. If I compare unicast to unicast, it's still not looking good. If I blow it up a bit, it's still not looking good. If I take the ratio, V6 is about 7 times worse than V4. That's not good. That's really, really not good. Shouldn't be there. So the summary, could do better. Report card, C-. Sorry, must do better. So on for the better news. Are you any slower or faster? So now what I'm looking at is the timing of the SYN handshake. Because when you give me back an ACK, that whole thing about shaking hands in TCP is not something that happens in your browser. It's something that happens in the kernel. And it's really hard to change its timing. So looking at that particular round trip time is the one thing that's actually relatively constant. There's nothing you as a user can do to really slow it down. So this is what I'm looking at, a single RTT sample per user. So what I see when I do this experiment is that when I hand out these URLs, one of them is in V4 only and one of them is in V6. And very occasionally, you send me back 2 connections. I've got you. I've got your V4 address and I've got your V6 address. And I've got the timing for both of them. So now, for just that small set of folk who can do V4 and V6, I can compare their numbers. I now am comparing apples to apples. And so I take the difference and I put them into buckets. And this is what we saw in 2012. The blue is what we're worried about, which is unicast. If there's a huge bulk over to, God, I always get this confused. My right, your right, my left. We're there. If there's a huge bulk over that way, V6 is slower for most folk. If there's a huge bulk over the other side, V6 is faster. And it's pretty clear that all the red's over to the bad side. Teredo is always crap. There's 6-4 in green, it's all over on the bad side. And the blue was sort of, well, more bad than good, but more central. That was 2012. What about this year? I'm hard-pressed. You know, I just can't figure out what's fast and what's better. But, you know, maths to the rescue. 6-4, by the way, is crap. Beyond Hopgun Redemption. Do not use it. Have you got the message yet? When I compare the two, 6-4 is still crap. But the blue is what I'm interested in. And there's one way of doing this that makes it a little more obvious, which is a cumulative distribution function. So basically, this is the number of data points that are worse than a certain point. And what you find for unicast is that most of the sample points are dead set in the middle. So what's this cane? Let me blow it up a little bit. This is the middle 40 milliseconds, just 40 milliseconds. So 44% of the time V6 is faster and 56% of the time V6 is slower, but only in 32% of the times is V6 more than 10 milliseconds slower. So for 76% of the time, V6 is humming along as fast as V4, if not faster. So that kind of tells me that most of the time V6 is keeping it right up with V4. In terms of speed, yeah, about half the cases within 10 milliseconds or more. So speed is just fine. 6-4 is shit, but I told you that. You should know by now. Is it as robust? Well, the answer is obviously no. There's something really bad about V6. Now, there's a combination in V6 that makes this toxic. I will point out Broadcom, not because they're the only folk who make rat shit V6 chips, but they're one of the larger manufacturers of chips inside CPE. And Broadcom hardware gets incredibly confused with bits of 6 in some models. So sometimes it's not the network, it's your device that will happily let the packet out, but gets horribly confused when the packet comes in, and there's nothing you can do about it other than buy a CPE that doesn't use that particular chipset. Cisco. If you do that, life will be a whole lot better. Sorry, but it's true. I didn't mean to do that. So part of the issue with V6 and reliability is your local equipment. And you really should look and think hard about what you use. Buy chips and hardware and open WRT and put the stuff together. You'll enjoy doing it as a geek. It's really a lot of fun to play with. And you're in control of your destiny and you actually get a decent service out of it. Because part of that awesomely bad problem is in the fact that the CPE is using really cheap chips. As for the rest of it, there's a deep and underlying problem with connection asymmetry in the internet. Not everyone sees the same internet. And when you do these massive experiments that span a huge amount of the network, what you see is not everyone can see everyone else all at once. The connectivity is actually more broken than we thought. And maybe we should do something about that too. So, quite frankly, if you can make a connection in V6, you're probably a happy little Vegemite, as we say in Australia. I'll explain that if you don't know the reference. But nevertheless, yes, V6 is as good as V4 as long as the connection starts. But the odds of making that connection, unfortunately today, across the world, the odds of doing so are still heavily weighted in V4's favour. That's it. I think we've got a couple of minutes for questions. If there are any, I'll happily try and answer them. Thank you.
Hi, Geoff and Johan. Two quick questions. The first one is on 6-4. Is it 6-4 on both sides, or does it go through a relay?
6-4 is that wonderful kind of automatic tunneling protocol where you, the 6-4 client, put your V6 packets inside a V4 header and go to some helpful person, you, who take out the encapsulation and send me a V6 packet. Now, I can't get to you in 6, so I send the V6 packet to a helpful relay, thank you, who then tries to get it back to you in encapsulation. Our packets have gone all the way around the room, and that was just a small example. Sometimes it gets horrendously bad, and debugging this is a skill and an art form. We were running 6-4 in APNIC, and I was wondering why all my 6-4 packets were coming through Christchurch in New Zealand. Maybe we just love the place. Maybe they're friendly people down there. I have no idea. But, you know, that's what happens in this kind of autonomous tunnelling. So that's part of the big problem, yes.
Yeah, the problem is really the open relay that you need to use between the 6-4 world and the real IPv6 world.
Right. It was often said that 6-4 relies on the kindness of strangers, which is a really crap way to build a service.
And my second question is about when is V6 faster? Does it have anything to do with the degree of connectivity that is somewhat artificially higher today in IPv6 than in IPv4?
So there are two issues of why V6 would be faster. This is an opening SYN of a packet addressed to port 80 or port 443. If you write middleware, this is what you eat for breakfast, because this is the stuff you intercept and capture looking for the next packet to try and find out what's going on, etc., etc. And if you're a middleware person, you don't bother writing middleware for V6 because no one uses it. You concentrate all your effort on this whole deep packet inspection in V4. And to some extent, it's not that V4 is, slower in terms of speed of light. There's just more crap on the wire that understands that V4 SYN is a packet of interest. And that what you're actually seeing that would make V4 slower is the act of interception and holding.
So when V6 will be mature and we'll have the same DPI
You'll have the same
stuff,
middleware crap and it'll all get slower, and that's the world, isn't it?
Thank you.
Did I just say that in my out loud voice? Sorry.
Hey,
Hey.
Kate Pearce, Cisco. So looking at the, good laugh. Looking at the metrics, do you have any measurements for when V6 works and V4 fails? Hosts that are reachable via 6 but not 4?
I probably do. It's an enormous data set. I've never asked that question of the data.
Could you ask
It is
before?
no, it is a fascinating question, because I truly suspect that a lot of the V4 failure is actually due to asymmetric routing. And whenever you look hard at routing, you see everyone has different route sets. So it's quite reasonable at times to think there's a V6 connection that's just fine and a V4 connection that's asymmetrically broken. So I haven't looked, and it's a great question, and you've just prompted another week's of work, so I thank you humbly.
Well,
I think.
I ask because I've seen cases where the V6 address auto-configures, but the V4 falls over and dies.
And in terms of this whole happy eyeballs dual stacking, if you've got it right, and certainly the Macs have got it right, Windows eventually got it right, Chrome gets it right, if one fails, you've got this other protocol just sort of almost half up, and you never notice that kind of brokenness, as long as everything's dual stack, just works just fine. When we ever get to turn off V4, all the ugly little warts will appear again going, hello, I've got a problem. But yeah, dual stack kind of defends us from that.
It's like you're introducing my talk.
Sorry, yeah.
Hi, Geoff. This is Gaurav, Limelight Networks. Have you ever looked at the packet size of your ads? Because in my experience, what we've seen when we enable V6 for some of our customers is invariably it comes down to the V6 coming over a tunnel from somewhere and the packet size getting crapped in there and fragmentation not working, and then suddenly their V6 is not working. We haven't done any instrumentation around it, but we just turned V6 off for them for a while and then hope it goes away.
In this particular experiment, I was being as nice as I could to V6. So all the packets are absolutely tiny. The opening handshake, the get command, and the resultant one by one all sit comfortably under 1 kilobyte of packet. So I'm not stressing anything. Have I experimented with monster packets? Oh yes. Are there answers around V6's handling of path MTU? Oh yes. It's not a pretty story.
Would be
but not
interested.
for here, not for now. But no, big packets in 6 are a problem.
I'm not on the APRICOT PC anymore, but I think we'd really like to hear that in the lightning talks if you have anything to talk about that.
I've got other things to talk about there, but if you are running a v6 service, look very, very hard at the way Google set up their service and emulate it if you can. It's a small price to pay, but set your MTU to 1280. Don't set it at 1500. Try and avoid fragmentation, even in TCP. Your customers will thank you for it. Because if you set your MTU down, there's less of a potential issue with MTU mismatch and the black hole of death. So yes, set your MTU down. Probably the last question here. Thank you.
It's Nathan Ward here. I wonder if you could do some testing with a Teredo relay, respond to half of your request with a Teredo relay local or a 6-to-4 relay local and see if it's because of the protocol or whether it's the relay. With 6-to-4 you probably can't get as much information, but with Teredo you would be able to because it should in theory detect your relay.
So the data that I gave you from 2000,
do you care about the results of that?
the data that I gave you from 2012, both relays were underneath my nose, sitting on the same machine.
Right.
So I was the 6-to-4 relay. I was Moredo. That was as good as it gets. Anything after that was infinitely worse. So what can I say? We tried that. Didn't make it any better.
Interesting. I also note that your Teredo numbers are low. I presume that they are all non-Windows machines?
What's left in Teredo are the diehards. Thank you very much. You can stop now. It's all over. Go and use native. Thank you. Thank you very much.
Thank you very much. Thank you, Geoff. I just realized I didn't introduce myself. This is Yoshinobu Matsuzaki, by the way, working for ISP and one of the co-chair for APOPS. So next up, next up here we have is Catherine from Cisco. She will talk about multipath, multiplexed, and multilateral transport protocols.
Yeah. All right. Lapel mic, please. All right, she's on? Good. Okay, so in some ways that previous talk was almost a good introduction to mine. The dual stack stuff, the various asymmetries, but we'll get there. Slides. Okay. All right. So, previously, we were just talking about, is it faster? Does IPv6 work better than IPv4? And there are some changes to protocols that mean maybe that question is moot. First of all, who am I? Well, Kate Pearce, SecValve on Twitter. Feel free to pictures, yell at me, whatever, tell me I'm wrong. This is a conference. I'm a customer-focused security consultant at Cisco, so I either break into their systems or I help them fix them. Break and report. Sometimes I'll sit down with a developer. I will help them go through things. Loud and yellow, or maybe that's a loud yellow. And just because, to be clear, this is all me. There is no official corporate representation in this. Okay. This is based on some work I've done previously on multipath TCP. Some extensions to TCP which fundamentally change how it actually works on the wire, but also how it functions as flows. And also extending some of that stuff to quick UDP connections that still transport this HTTP traffic. Again, breaks things. So a simple example with multipath TCP first, open up a curl connection to a server. Okay, we should all know what that should do. We pull it up in Wireshark, and the response is missing, even though it came back. Well, why is that? It's very strange. Or another simple example would be if we open up Netcat. So we open a single connection to an IP address on port 3000. Again, we should expect to see just a single IP address connected to, but that's not what happens. We have rather a larger arrangement. Also, there's a couple of V6 addresses in there as well. One connection opened up 10 flows across both V6 and V4. That is very weird. And that is why we're here, to talk about some of the upcoming transport protocols and how they change the way your networks behave. So sort of the way I'm going to go through this, some background into what TCP is and why we want to change it, discussion of multipath TCP. And then there's also some reasons why you wouldn't necessarily want to change TCP, why you may want to go with another option. So I'll talk quickly about them before diving into QUIC. And then sort of a bit of a discussion of what that means and some takeaways for you. So for the background, as we will discuss today, we have a scale explosion of the internet. We have an increase of hosts, increases of interfaces per host, increase in applications per host, and an increase in connections per application. So we'll increase in host count. Okay, we put out more addresses. We'll put in carrier NAT if that doesn't work. An increase in our applications per host, throw in more compute. Or connections per application. It changes on the application, but there are a few things we can do. But how are we handling the increase of interfaces per host? And that's where the multipath techniques come in. Why do you care about this? Well, some of these problems are very familiar. Address space is exploding, your route tables are exploding, but there's also some interesting new problems. As you're opening up more connections, the amount of state you have to track in your network translation explodes. And if your clients are controlling where they are sending packets, you can no longer use route tables in the same way to decide what goes where, because your client is deciding on the basis of its visibility and not your decree. And that can get messy. To be clear, personally, I love these technologies. They're more culture shock than a direct problem. But by and large, everything I throw them at either doesn't see them or falls over twitching. Has no idea how to deal with this stuff. So, current TCP doesn't support use cases for high availability, link aggregation, multi-homing, or mesh networking very effectively. It also makes a lot of round trips, as discussed earlier. SYN, ACK, SYN-ACK, 1.5 round trips to set up that connection. If you're doing SSL as well, it goes dum, dum, dum. It's sort of it several times as it sets up the different levels. And TCP blocks streams because of the way it handles its acknowledgements and its negative acknowledgements and selective acknowledgements. So people end up opening a lot of different connections to try and pipeline that way rather than going through one single connection. MPTCP deals with those top four. QUIC tries to deal with the bottom ones. Why is this all happening? Well, networks need multipath, but there's more than one way you can do it. You can do it at the transport layer, and after all, we've all been using quite low-level layer 2 solutions for this for quite some time. But there's more than one way to do it. Multipath TCP extends TCP to add that multiplexing. QUIC ignores TCP and does it itself. Key thing to remember between those two protocols. But as I said, they fundamentally change the way hosts talk to hosts and flows happen on the network, and that the internet behaves as a whole. Okay, so multipath TCP, let's dive into that a little bit. What are these extensions to TCP that are getting added? Well, I said earlier that TCP doesn't do some certain things, and multipath TCP adds to deal with those. So it adds in that multi-homing, that mesh networking, the address mobility. It works over existing infrastructure. It is an extension. It's a TCP option sitting in the TCP header. It is TCP traffic with additional binding information to bind those streams together. And nothing really understands it. There are a few things now, since I first did this a couple of years ago, but by and large, this is mostly ignored. But by and large, it's not mostly used. The main thing using it at a scale is Siri. And I've known a few customers to be particularly worried about that. But by and large, it's just interesting. It's not seen as scary or frightening. But every macOS device, as of a couple of versions back, has this into the kernel. You can see the options there. You cannot open a multipath TCP socket because of how they've protected it, but it's sitting there. Presumably Apple's going to do something with it. I don't know. But if they decide to switch that on, we've immediately got tens of millions of devices trying to use this. In addition to the hundreds of millions of iOS devices already using multipath TCP for that limited use case. So TCP implements connections, the normal tuple, an IP and a port at one end to an IP and a port at the other. Networking 101, very, very basic. And in the original specifiers, it treats it as without regard to path. I'm going from there to there, I don't care how I get there, that is the network's problem. That is not an endpoint, that is not a host, it is by and large an interface, an IP address and a port to an IP address and a port. In the past that hasn't mattered much, but by and large it is mattering more and more and more and more and more as we go forward. Because you can't go using address mobility or roaming if you're trying to define your endpoints by IP address. So it sits on top of TCP, it extends it. It puts a connection ID in the header. That is how it binds them together. Anything belonging to the same connection has the same connection ID. A multipath TCP connection has normal TCP subflows with their normal TCP sequence numbers and setup. And it just binds them together using that option. Has some characteristics. It is backwards compatible. Because it is an option, you strip it out, it'll just fail silently. They aimed for the performance to be greater than or equal to an hour. From what I can tell, it is, because most of the worst cases involve it getting ignored. And the security greater than or equal to an hour. TCP is not exactly a secure protocol, so that's not a high bar, but that's where they were aiming for. Simple case, a multipath TCP connection between the host on the left with 2 interfaces to the host on the right with 1. We open up our first subflow, it's a standard TCP connection. All right, we open up we have a second network. We go through that. Okay, so we have 2 connections. They are bound together using multipath TCP. And if we want, we can actually send them across the same path. It doesn't care. It is just, you give me streams, I will join and bind them together. You can map the data however you like across those subflows as chosen by the sender. That'll get important even more later on. The packet sender decides what data goes where. If you drop some of them, it'll keep going as long as some of them are still going. You have to kill every single one to reset these connections, because it can re-add them and keep going. If data's not active, it'll acknowledge across a different path. Again, these are some details, but it's not as easy to, when I was in the States, they had the concept of whack-a-mole. This is what you're doing with a network. Bang, 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 bang. You've got to try and get them all, and you can't do it fast enough. It behaves very differently. But very good to a mobile client, very good to a data center. Mobile client for roaming, because it can add and remove addresses as it goes. Good for a server, because it's like, I have all these links. Let's bind them together and aggregate the flows. So it can use whatever available throughput it has between those paths. As I said, it's a TCP option, so it sits between the standard TCP header and the packet data. It's all in the RFC, but there is a lot of detail in there if you really want to dive down. Wireshark supports this, so you can just open it up, dive in, and it's sitting there, decoded for you. In Linux, so to give you this concept of paths, the Linux Path Manager has a couple of different ways it defines how to connect between hosts. This is just in the Linux implementation, which is the easiest one for you to get and to use. So this is all done in the TCP stack. You open a connection, it opens a connection. What you don't see is underneath, it's opening as many as it needs to set up that multipath properly. So I said that there were the end of ports. So along one path, it just sets up n numbered connections. Okay, that's not too bad. But full mesh is where this gets interesting for your network management. That is one connection. It's one valid connection with no duplication of paths. Not at the network layer. And that's an explosion. That's a lot of state explosion. Okay, so multipath TCP goes about it that way. Why would you not want to change TCP? TCP is well understood. Why would you not change it? When Google have worked on Quick, they've said there's a few reasons. There's some things I learned from multipath TCP specifically. It was very slow moving. You need to get that vendor support. If you don't have the vendor support, no one really cares. Multipath TCP had a lot of middle boxes meddling, trying to change things, sometimes for good, sometimes for bad, sometimes for security, sometimes for performance. But the effect is, when your clients and server expect one thing and the network is changing things, it can cause inconsistencies. So as I said, the deployment. Vendors don't want to put it in their kit because no one's using it, and no one wants to use it because it's not in their kit. Google has a bit of a solution to that, which I'll get to later. Some other things why you want to change TCP are the characteristics of TCP itself. That handshake design, SYN, ACK, SYN-ACK, boom, boom, boom. Every time, that is just the way it is built. TCP is done in the operating system, usually, but it's outside user space. And it blocks as it's waiting for retransmissions, and it can't just say, I'm going to ignore that and carry on. It has to get it, or it blocks. Well, if you can't change TCP, what's left? Well, the obvious thing that's left would be, no, SCTP, it had some cool things about it. It was really complicated to deploy on a network, as a few of you will have seen, and it never really took off at scale. Okay, well, what else is there? UDP? Well, yeah, there is. But UDP doesn't do anything exactly. UDP is a dumb packet sending protocol. And that is why they chose to use it for Quick rather than messing around with TCP. There's complexities changing TCP. UDP just naively goes on its way. Okay, so you don't want to change TCP, you do want to use UDP. Here is a solution Google has come up with in Quick. Quick is really complex, even compared to multipath TCP. So I'm going to do a bit of an info dump at some point here. We can talk about it afterwards, but don't expect to follow it all. Expect to catch something interesting and look into it later. Quick stands for Quick UDP Internet Connections. And you thought multipath TCP developed really fast in a couple of years. Quick's been frighteningly faster still, a lot quicker. It's already in a lot of Google properties. And if you look at UDP 443, UDP 80 traffic on your network, you're probably seeing a few percent, just from Google properties alone. Okay, current TCP is rather limited. Does lots of round trips, and it blocks on retransmits. That's the stuff Quick is trying to deal with. So, it is a UDP transport protocol. Google champion successor to Speedy. Latency optimized. I'll get to that in a second. But it's more worried about dealing with that latency than anything else. It is reliable. It deals with retransmission, congestion, and all of that. It is multiplexed. One connection has multiple flows within it. It is always encrypted. Good luck changing this. It's open source. It's in the Chromium source. User space, so there's no operating system requirements, and it's fast evolving. Every Chrome browser that you have will have this in it, and many of them will have it turned on, at least for Google properties, and possibly for all properties. The stuff is there, and it is live, and it is going. When you own both the client and the server, suddenly you don't have that chicken and egg problem. Latency reduction. The primary aim of Quick is to cut down that round trip time, particularly on long pipes. When I moved back from the States to New Zealand, I really noticed that, because I've gone from getting 5 millisecond round trip to, 180 minimum? And when you do that, and it's just a secure connection, and then it blocks on the HTTP, and it can be a few seconds no matter how fast the server is. So that's what they want to do, to try and get that to 0 round trip time. What does that mean? It means you send a packet, and the connection immediately continues. You can send data with your first packet, and that packet also contains enough data to set up a secure encrypted channel. Or one, if certain conditions happen and it doesn't want to, it's just boom, boom, okay, you're good, go. Rather than going back and forth and back and forth and back and forth and back, okay, well, which encryption protocol back and forth? No, it just goes. And that's why the users like this stuff. It really does make a noticeable difference. They've put in forward error correction. So if you lose packets, it rebuilds them and continues on. No blocking on a missed packet within a block anymore. Flow control, all built into this. This is basically a replacement to TCP, only more so. Certificate and header compression, again, just to cut in that latency a little bit more. Google claims 30% reduction in video rebuffers. That's a huge amount for a user. Huge difference in user experience, and a 10% reduction in page load times. Overall 10%. The 99th percentile was a little different, but they have some really fascinating statistics on this. Just changing the protocol slightly and decreased latency, a huge amount. Okay. Quick connection, UDP port 80, UDP port 443. Info dump. So, I'm going to throw a lot of the concepts of quick at you and see what sticks. Some of you will be interested in different things, and we can talk about that later, or as time is appropriate, but there is a lot of data in these next few slides. Okay, quick is not simple. Read the RFCs, read the documents, read the source code. It is way more intricate than multipath TCP. As it gives you control of a lot more things. As I said, I'm going to race through. Okay, packet types. Quick has a packet, of which you can have a regular packet or a special packet. Those packets have some structure, a UDP container. Within that UDP container, you have a quick public header. The public header is not encrypted, but it is authenticated. That is the primary quick public header underneath the UDP header. Under the UDP header and quick header, you have some authenticated and encrypted data, that red block, which within it has a private header, which is both encrypted and authenticated. And within that, under that private header, you have a frame packet. That frame packet can contain multiple frames. Protocol within a protocol within a protocol. Top bit is authenticated but unencrypted. The bottom bit is both encrypted and authenticated. If you're managing your network, you're only going to see that top bit, and you can't change it. Other than the UDP header, you cannot change that quick public header, or it will start failing authentication checks. One quick connection. Okay, this has gone to a weird order. Let's build that up. One quick connection contains a number of streams within it. One quick packet contains a number of frames within it. Well, one quick packet can contain a frame packet, which can contain a number of frames. Protocols within protocols within protocols. It is turtles all the way down with this. There are two primary parts to a regular packet. The public header, the private header, the headers. Wait, I have no idea what I was saying here. Move on. Okay, headers. We have a public header, which is authenticated, not encrypted, containing flags, connection ID, packet number, version header. Packet number is not the sequence number, that is different. And you also have the private part, which contains flags, error correction, and a frame or a forward error correction packet. Different headers, visible, invisible. Okay, so then we have a frame down in that. And that frame contains some number of, the frame packet contains some number of frames. Or it's a forward error correction packet. So error correction is actually very elegant in this protocol. They define a block of packets, they XOR them all, and they send that XOR to you. So any packet in that block goes missing, and you have the rest, including the XOR, you can just, boom, reconstruct it. And it doesn't define that length. So you can tweak that length block and that error correction block size. The private header controls the details there. Frame types. Lots and lots of frame types. So the frame is, so it's UDP, quick, frames within that. And within that you have another protocol. Frames. The ones that, simplest ones are the stream and the acknowledgement. The rest are various control frames largely. Stream frame, which is where the data is sent. It's contained inside a frame packet. So you have a frame packet which has frames within it, and they can include stream frames. A stream frame itself has a type, a stream ID, an offset, and a length. It is multiplexed. This is one of those internal channels. An acknowledgement frame, also within a frame packet, not necessarily with any others, but, you know, it's a packet. Again, type, the largest observed packet number. What have I seen up to? The acknowledgement delay time, it uses that for congestion calculations. Timestamp section is much the same thing. It stamps packets as they go out, and it tracks various network metrics as they transit the network. Uses that to calculate on the fly how it's sending them, what the window sizes are for both stream and connection level. Missing packet, you know, it's an ACK. I didn't see that one. Or which ones it revived but didn't see. Addressing. Much like multipath TCP, you have a connection ID, an implicit address that is used to associate that connection to its peers, to the rest of that connection. It is independent of network address. You can change your network address and continue your connection on, as long as your connection ID is valid and a couple of cryptographic details. That's what the source address token is. The source address token is a secret you have shared with the server that proves that you can receive on that path so that you can't do a simple reflection attack. Stream ID is what you associate those stream frames. You're like, this one goes to that stream, that one goes to that stream. It's the multiplexing. Cryptographic. It replaces and is comparable to TLS. Next version, TLS, actually is far more similar. IP spoofing protection. It checks that you can receive on a path before dumping data at you, so that you do not get those reflection attacks. Not trivially like you do in NTP or DNS. I'll have to look into it more, but it doesn't look like there are any trivial reflection attacks, which is good. I don't want to get web servers doing reflection attacks as well. Okay, error correction, extra reward packets, block size is variable. If it's revived, I didn't see that one, I revived it, continue. All connections are assumed to be in open state. There is no connection open or connection close. It's just like, just leave it open. And address mobility is supported. It's quite happy for you to change as many times as you like. It'll maintain that connection open. No reestablishing. Multipath is planned, much like multipath TCP, but it's not quite there yet. They're still working on that. If Quick goes multipath, our network monitoring, our packet inspection is in real trouble because it's fully encrypted, unlike multipath TCP. Because it was designed to handle HTTP traffic with HTTP2, it's going to abstract out some of that and deal with it itself. Now, for this to work on your network, these are Google's recommendations. UDP unicast, unimpeded. Don't mess with your UDP. Most people don't mess with all UDP. No filters, no rate limiters, and to set your timeouts to a reasonable value. If your timeouts are really short, it's going to send it out and it's going to bounce. If it's really long, you're going to have a lot of state staying open. Okay, as I said, info dump. If you want to see this in your browser, the simplest way is get a Chrome browser, go to something like YouTube or Google, and go to Chrome Net Internals Quick. It's right there. That gives you Chrome's versions of it. You can also pull it up in Wireshark, and all of the unencrypted aspects of it you can see, and there's quite a few of them. All right, so anyway, what does this all mean? What's about multipath or connection mobility? What is about this stuff and how does that affect your network? Well, when they were designing these things, were they thinking about the network environment? Sort of. With multipath TCP, they were more thinking about what they were building and protecting it from attackers. And they did a pretty good job of that from what I can tell. What they didn't consider quite so much is the way that people are doing network security or network management, a lot of which is inspection, a lot of which is modification, a lot of which is various forms of coalescing, binding, merging, unmerging. And that is sort of where multipath TCP made things fall over because it looks like TCP. If you don't understand it, it's just TCP where the data doesn't make sense. Quick was much better at this. They put far more thought into that. What is hilarious, though, is because they want this traffic protocol to succeed, they've done some changes to it to ensure that it won't be messed with by network operators. And that's why it's fully encrypted. That's why it's authenticated. They don't want people changing it. You can NAT it, anything other than that, and it's going to start falling over. It's just not going to work. So these protocols are sort of designed to mess with much of the stuff we do, but there's some more fundamental stuff as well. Okay, so all this talk, what does it look like on a network? Well, that is a single Firefox browser going to a single web page via a single web proxy. And every one of those lines is a connection, every one of those blobs that is insane. That is a lot of flows for one operation. Well, if you start clustering by IPs, because you know which hosts have which IPs, still doesn't, which IPs connections are clustered together. It makes a little more sense, but it's still kind of a spider web. And once you start understanding how the multipath is working, you can see it's just fragmenting. The way I've taken to describing this lately is, a lot of us will be familiar with fragmentation attacks or fragmentation problems, where linearly through time you are breaking your packets up so that the packet boundary breaks across some, maybe a signature. This is two-dimensional fragmentation, not just time. You're also breaking across paths. Okay, so for your network management, it gets even messier still because these are agnostic to what's underneath them. As in the first example, IPv4, IPv6, it doesn't care. It's got a path, it will use it. As you saw in those diagrams, if your tool does not understand multipath TCP, they can't associate quick, or whatever multipath protocol you're using, you just see a lot of arbitrary connections going out. If it's multipath TCP, it's TCP flows. If it's quick, it's UDP flows. We actually saw this earlier with someone. I was looking at a network monitoring system earlier today, where it had terrible trouble trying to determine what was a UDP packet and what was a UDP flow. So that cross-path fragmentation, very, very simple example. If that IDS is looking for A, B, C, D, it will never see it. If you have two of them, neither of them will see it. They need to have some way of synchronizing. And that's some of the changes we're going to have to make to our architectures if you want to do inspection, to synchronize across the various connections where you can, as I'll get to later. So, how would your carrier-grade NAT system handle it if your connection count exploded in addition to your address count? What do I mean by that? Well, if you have two devices and they each have one interface each, it's a one-to-one mapping for a single connection. If it's 4, it's 16 flows, potentially. As the number of interfaces goes up, as the number of devices goes up. So if you add in a third device, and they want to talk to each other, it gets even messier. This is yet another sort of addressing explosion and an explosion of state. What about your virtual interfaces on those hosts? What about your VPNs, your proxies, your load balancers? How are they going to keep track of all of these different things? Well, what if they don't see them? What if you've got mobile devices and some of it's going across a cellular network, some of it's going over your Wi-Fi? How do you manage that? Well, it gets a little messier still because with these techniques, but also these protocols, they don't have to be a direct host-to-host because you can start going through proxies or you can start bouncing through different routes, through different networks. If you can't understand it, you can't interpret it. If you can't interpret it, you can't make sense of it. How do you correlate connections when they're fully encrypted? In sort of trying to solve this address exhaustion with NAT, which by and large works in most cases, are we risking sort of exposing ourselves to state? The difference between a stateless routing and highly stateful routing, particularly when it comes to NAT, because you have to track every connection, every flow, what goes where, when, how long it stays open for, who it belongs to, have they moved? I don't know. It's a question to be thinking about, particularly if these techniques take off. A cell phone has Wi-Fi, Bluetooth, cell, and several other interfaces which can all do IP. If people start using them, that's a lot of connections for us to try and manage. So because of those things, because of the cross-path stuff, moving targets as people are adding and removing IP addresses as they move, or just because they feel like it, because those connections, until you can kill every little bit, it keeps going. Reverse connections is a multipath TCP thing I'll get to in a moment, but it's a bit of a mess. If your network management requires any of the things I'm about to list, which are very, very fundamental things, assumptions some people don't even realize they're making. That if you look at a TCP stream, you can make sense of that application data. That a logical session and an IP address are necessarily bound. That an IP address means anything with regard to a host. Or that you can tamper with, shut down, or close, reset bad connections. Or that you can differentiate clients from servers based on who connects to whom when. I'll get to that in a moment. That's what I meant with reverse connections. If you do any of those things, something is going to break as you move to these newer protocols. Some of the key effects. Cross-path fragmentation, kind of the whole point. They move, and they're resilient. All right, reverse connection's done. So, I said back, the packet sender decides which packets go down which path. Famous quote. One of the things you will see here is as we change traffic, it may detect it as damage, and it may route around it. Your attempts to deal with traffic by changing it, modifying it, delaying it, whatever, may simply result in you not seeing it anymore because it's going some other path. So I said earlier, if packet sender decides which data goes down which path, a normal or a benign client won't do really pathological fragmentation schemes. It won't go A, B, C, D, E, F, but we can. There's nothing actually stopping us doing that. Multipath TCP has a particularly fun feature, address advertisements. You can tell the other end, you can also get to me on this address, please connect to me on it. It changes things for perimeters a little. An outbound incoming connection. One is about the direction of flow, one is about the direction, one is about the direction of packets, one is about the direction of data trust, or data flow. You'll see. So, simple example. Multipath TCP opens up a connection, responds, okay, we have a connection. TCP connection. The client tells the server it has an additional address. The server connects back to it. Is that connection incoming or outgoing? I don't think that's necessarily the right question, but that's the sort of thing you get once you add address advertisements and multipath stuff. I'm still confused about that. Okay. obviously there are some positive implications on this too. Because if the packet sender decides, maybe it gets a bit more control over what it does, which can have potential privacy implications. Because those endpoints, I don't like you anymore, you've done funny things, or I'm just going to spread my trust across you. If I don't trust my ISP, I don't trust my cellular company, do they talk to each other? Do they fully synchronize all of my packets? If I encrypt it and then chunk it across different streams, suddenly there's a business problem in addition to a cryptographic or monitoring problem. Because you can require cooperation or large-scale sniffing for someone to make sense of your data. Okay. When people first saw this a while back, they said it's a problem of tools. No. It's a problem that only exists because of multipath TCP, which was the first thing I talked about. No, definitely not the case. It is actually far more pervasive than that. It is not just multipath TCP. It is not just quick. You can do this with HTTP. If you use range requests, I want half of the file there, a third of it there, and the remainder here. These things are a lot older than that, but it's not about the tools. Tools can be a help. They cannot solve the problem, inasmuch as it is a problem. As discussed a little earlier, originally the network's job is to transmit end-to-end, to work around damage. And, you know, seminal paper, 1974. Within each network, communication may be disrupted due to unrecoverable mutation of the data or missing data. End-to-end restoration procedures are desirable to allow complete recovery from these conditions. End-to-end. That doesn't give the network power. That gives the client power or the connection as a whole. So, our networking management approaches often rely on metadata, data inspection, content inspection, deep packet inspection, really, to try and understand what's going through. But the internet wasn't originally designed or built or engineered to support that, not as a whole. Within your network, you may be able to do that, but not as a whole. And so, you only control the packets for a part of their path. Someone else controls them for the rest. So the more technical takeaways. An address is not a connection endpoint. An address is a temporary connection endpoint. If you move house, you're still the same person, your address may change. State exhaustion has a real risk as we start seeing more and more connections, more and more devices, more and more paths, more and more interconnections. Maybe it's a tenable solution, but considering we had concerns around route tables, maybe not. What are you going to do if every single residential user opens up 200,000 connections? And that's their minimum. Multipath technologies break assumptions we may not even have realized we were making in the first place. They're really cool technologies. When you see them work on a phone or a laptop and it just, nothing drops out as it goes. It's really amazing to watch. It just keeps going seamlessly. But it breaks all of the business models, inspection models, network management models that, frankly, we've been doing for the last 15, 20 years. Longer in some cases. And whether you're network security or network management, in as much as you can prepare, you should do so. That may mean tools. It may mean simply knowing this stuff exists and saying something funny is going on. Could it be this? 5 years from now? Probably yes. Today? Maybe. Tomorrow? Is it going to Google? If so, yes. References and links will be available in the slides. All right, any questions? feel free to come and talk to me after. All right, do it.
So what kind of preparation can we take for as network management?
For which protocol or in general?
Oh, much path or much.
So with a device that you control the physical space of, try and make sure you understand all of those connections and where they're going. For a mobile device, good luck, because you have to control all of the possible interfaces if they ever connect anywhere. Particularly if you look at, it's analogous to a cryptography thing where if you have a small bandwidth channel, which is a very, very high security, you can use that to restrict access or secure other channels at a much higher bandwidth. So if you miss a 100 bit a second channel, but that's the crypto key, you're never going to be able to make sense of the rest. The other thing you're going to want to do is look for hosts that are particularly high on the connection count, particularly if it's not sort of BitTorrent style explosion, but is more concentrated. That'll tell you that this is probably what's going on.
Yeah, hi, this is Raphael from Equinix. So I can see this being useful in specific environments where I can improve throughput by doing multipathing. But in a general environment, we have actually invented a lot of stuff that would break this in the past 10 years or so. So an example would be like Anycast, right? You talked about mobile connection and Wi-Fi connection.
You move and it changes node. Yeah.
And then basically, if it's anycasted differently on those two different networks, your packets, one packet would go to this server and the other packet would go to another server completely differently. And there's no chance of that of the server sort of
So there's no chance if your server isn't aware. If your server has done some sort of synchronization.
Let's say I'm in the US, right? I have a Verizon file service at home, and then I'm using T-Mobile for my mobile, right? So basically, there's Google caches in T-Mobile. There's like Google, and they're all anycasting, right? So it's all 8.8.8. So my one connection goes to the cache on let's say T-Mobile's network, and the other one goes onto Verizon's network, right? So the server doesn't have a possibility of assembling that stream back into an MPTCP stream.
So with the specific example of Anycast, if you're going purely by IP address, yes.
Right.
If you were doing any sort of other, like you can do this with other protocols if it's binding to a particular one.
Right.
Anycast, yes, it'll break this.
Yeah.
But that doesn't mean that other people aren't going to use it.
No, I'm saying that it's useful for certain applications, but as a generic protocol you use for serving web content, for example, is going to break. So Anycast is one example. Another example would be load balancing, right? I've got load balancers that specifically hashes different streams to different servers.
So it's breaking because your load balancer is not aware. So if the client is just arbitrarily asking to connect, yes.
Right.
But if the load balancer has several addresses
Right.
that come through different pairs, that's when it gets interesting.
Right.
Particularly if you look at some of the arguments there's been back and forth about whether or not people are weighting different pairs in different weights, you can start doing route arbitrage,
Right.
where you pick the route that's not only fastest or most high bandwidth, maybe the one that's cheapest.
No, understood. I mean, I think the parallel separate streams is more compatible, but this is interesting.
It's fun. As you say, by and large, the application is not huge. Quick is actually a very interesting example because it's gone really quickly. But maybe you'll kill it. Maybe you won't. Maybe the user demand will be so high. Keep an eye out. And as I say, remembering that I do application assessments, I do penetration tests, I can use these techniques to walk straight through any firewall. Any firewall, any inspection. Because it has to know what to correlate where. Unless you're doing whitelisting of all of your traffic, you cannot make sense of it. Simple example I said earlier of HTTP. If I want to download a malicious binary, and I know that they're running something that will download that and analyze it, I request half from here and half from there, but I set the server to never give a full response. And immediately, how do you do that as an inspection on your network? It's just not a paradigm we've been used to. Anyone else? Oh, hello.
Martin Levy, Cloudflare. Your basic assumption is that you actually want to look at traffic. I question that.
So that is the assumption with some of the stuff I was saying, yes. Some of the nuances I didn't get into a whole lot are you get things when you start changing QoS down paths where your clients may decide to swarm or to change paths on you.
You're assuming that you want to do QoS.
I'm assuming you're doing something other than routing packets.
I would contend that in some cases you shouldn't be.
I would argue in most cases you shouldn't be.
Thank you.
But the fact is, a lot of our business models rely on changing things. I argue, yes, the internet was designed to go from end to end. That's not the way it actually works. Whether it should is a different question, which is more philosophy and closer to religion in our circles.
So this is Geoff Huston, and I'd actually argue that what you're talking about is a question whose answer values in billions of dollars. What we see in the mobile spectrum space is hideously expensive connectivity services. Yeah. And what we see in the Wi-Fi space is phenomenally cheap connectivity services. And the real question is, can I flip seamlessly
yes.
from expensive to cheap
yes.
and keep things running?
Yes.
Now, if I'm a mobile carrier, the answer is no. Hell no. Never.
Exactly. And who has the biggest stick?
But if I'm Google and I don't operate one of them, then I'm getting interested if I'm taking the customer's side. And even if I'm Apple, if I have control of that really expensive switch, can I arbitrage between Wi-Fi and cellular, and who's going to pay me the most?
Yeah.
So the reason why this is important, it is a handset argument more than anything else. And it's actually an argument about what we call handoff.
Yes.
And being able to control that handoff, whether it's the application running quick, whether it's the driver running multipath TCP, or whether it's the underlying drivers in the handset itself, becomes this phenomenal question of control. And that's why I'd contend, Martin, it's actually a really expensive question, and the answer is really expensive, and it has nothing to do with QoS. Yeah. It has everything to do with my wallet. Thanks.
It does, and particularly if you're doing data metering, as you say. But there are other advantages if other things concern you more, whether that's security, whether that's latency. You can do things that we're not used to. But yeah, money is what matters. Samsung has deployed this in a couple of carriers in South Korea for their Galaxy handsets. There is a solution available from an ISP in France that will do multiple internet connection binding via these techniques. You set up a proxy at one end, shove that box in your house, it will just use whatever connections are available to the house seamlessly. They go up, they go down, whatever, it'll just go. The user experience is phenomenal. Facebook doesn't drop out if you're on weak Wi-Fi, it just goes. Maybe we will get the problems which Apple had with the Wi-Fi assist, where people were on the edge of Wi-Fi, and so the phone seamlessly switched and started pumping it through cellular while being connected to Wi-Fi, causing huge data bills. Maybe we'll see that. But no, this is all going to come down to business models and money, and who has the biggest stick and what the motivations are.
Now, thank you very much. Okay, this is an ending of this session.